Hey guys, welcome to this video. In this video, we're going to be talking about SVD. So we're going to be deriving it from scratch, and I'm going to show you the exact mathematical derivation of it and why it's useful. So before we get into it, there are certain prerequisites that you have to cover. So one, you need to know about eigenvalues and eigenvectors and how to calculate them and what they signify as well as a bit of derivative calculus. So this derivative calculus comes in handy when we're doing the derivation and how we get the formula for SVD. So let's get right into it. So here is the formula for SVD. So SVD, if you guys didn't know, stands for Singular Value Decomposition. So A is a generic matrix M cross N. It needn't be square, it can be rectangular as well. So that's one of the advantages of SVD as compared to standard diagonalization. In standard diagonalization, one, it needs to be a square matrix, and two, you need to satisfy the condition of diagonalizability. But SVD works for every single matrix, there's no exception to that. So A is your generic matrix. It can be M cross N, it can be N cross N, rectangular or square, it can be whatever. U is an orthogonal matrix. Excuse my handwriting. Of the eigenvectors of the matrix AA transpose. So U is orthogonal matrix and it comprises of the eigenvectors of AA transpose, normalized eigenvectors. So that means the length of the vector is 1. V is also an orthogonal matrix. And it comprises of the eigenvectors of the matrix A transpose A. And sigma is a diagonal matrix comprising of the singular values of A. So the singular values of A. What are the singular values of A? It's nothing but the square root of the eigenvalues, sorry, of either A transpose A or AA transpose. So if you guys didn't know, the matrix A transpose A and AA transpose will have the same uh, eigenvalues. But by same, I mean the same number of non-zero eigenvalues. That's just a fundamental property. So yeah, so suppose A transpose A or A transpose have lambda 1, lambda 2, and lambda 3 as, say, the eigenvalues. So the singular values would be, I'll just write the matrix itself, why not? So your sigma matrix would just be square root lambda 1, sorry about that, square root lambda 2, square root lambda 3, and since it's diagonal, the rest of the entries will be 0. Okay, all of this is great, but why do we need SVD and how exactly do we even get this formula? So I will be deriving that now, and I'll show you exactly why we need SVD as well towards the later part of the video. So let's understand the derivation with the help of an example. So here on this graph, we can see we've got shoe size and height, and we've got our points plotted over here. Now, for simplicity, what I'm going to do is I'm going to centralize the data. So consider this as mean centralized. So now what we want to do is we've got our matrix. Let's call our points, the centralized points, matrix A. So there are n points and each have 2 dimensions. So this is our data. We've got A, which is n cross 2. So now what do we want to do exactly? So we want to find a vector, a unit vector, such that when we project our points onto this vector, so let's take this vector. You know what? Let me change the color for this. So what do we want? So we want a vector and we want the direction, a unit vector, such that when we project our points onto this, we get a maximum variance. So by projecting our points, let's just call this vector v. So this is the vector that we're trying to find, and we need to project our points onto that. So in order to project our data points, we simply just do AV. So V will be 2 cross 1, and A, as we know, is n cross 2. So our resulting is an n cross 1 vector of these projected points. So our goal is to find a vector such that we maximize the length of this vector. So why do we want to maximize the length of AV? So we know if we project these points onto this line, so let's say we project it. Let me draw this separately. So say this is our vector that we've gotten here, and these are our projections onto this vector. So now if we look at this, if we find the length of the vector, it actually tells us the spread. So that's why we want to maximize the length of this vector. By spread, I mean the variance of the data. So our goal is to capture as much and maximum information as possible. And we want to subject it to the constraint that V transpose V is equal to 1. And V transpose V is nothing but the length represented in like a vector notation. So the length of the vector V is nothing but this. So the length, is nothing but V transpose V. So we want to subject it to this constraint. And I'll explain why we want, we're going to subject it to this constraint, because one, we want only the direction. So we want to know just the direction of it. We don't really care about the length. Plus, when solving for this optimization, we're going to use Lagrange multipliers. You don't need to worry about what that is and everything. That's all right. It's just a technique to help with this optimization. But without this constraint, you can see that the optimizer can cheat and we'll never really achieve our goal. So I will show that also later. But for now, let's not worry about that. So similarly, if we follow the same thing, we know that I just showed you. So to calculate the length, V, it's nothing but V transpose V. So our goal is to maximize AV. So we can simply rewrite this as AV transpose AV. So when we have something like this and we have a whole transpose, we have to invert it when expanding it. So it'll be V transpose A transpose AV. So our goal is to maximize this. So let's use Lagrange. So we know L. So this is the multiplier, lambda and V. And since it's maximization, we need to do V transpose A transpose AV minus lambda V transpose V minus 1. Again, you don't need to worry about this. This is just how Lagrange multipliers work. So what do we need? So we want to find del L by del V. So this ends up becoming 2 A transpose AV. So the derivative of this with respect to V is nothing but this. This is just a formula. You don't have to worry about how it's gotten. Yeah, and similarly, if we take this term, so this is going to be del of lambda V transpose V by del V. And we can consider V transpose V as, one second, before that, let me finish expanding this, minus lambda, del lambda by del V. So V transpose V can be written as V transpose IV, like where I is the identity matrix. So these two are one and the same. So essentially, what this term will become, it'll just be, and since lambda is a constant, we can just push it out. So this will just become, I'll write it here, 2 lambda v. Well, technically 2 lambda iv, but that's the same thing. And the derivative of a constant is always 0. So essentially what we end up getting is this. So we've got our del L lambda comma v with respect to v as 2a transpose av minus 2 lambda v. Now this we equate it to 0. Again, this is just a step of Lagrange. You don't need to worry about the exact reasoning behind it. So essentially our equation boils down to this: a transpose av minus 2 lambda, minus lambda v is equal to 0. Does this expression look familiar? Let me rewrite this again. Let's move this on the other side. Is equal to lambda v. And if I put a bracket around this, look at that. We've essentially gotten a transpose av is equal to lambda v. And if you consider this, and this is a matrix a transpose a, we know that. And this is lambda v, where lambda is a constant. So from this equation, we can see that these are the eigenvalues and eigenvectors. So v is your eigenvector and lambda is your eigenvalue. So the entire problem that we boiled down, the optimization, the solution to that is nothing but the eigenvectors and eigenvalues. Isn't that crazy? So these are the eigenvalues of A transpose A. Note that, not just A, but A transpose A. So we need to maximize, as I stated before, V transpose A transpose A V. So we know that this is nothing but lambda V. So we are maximizing V transpose lambda V. And since lambda is a constant, we can push it. So it's maximizing lambda V transpose V. Since it's a constant, that's why we can move it here. But we also know our constraint that V transpose V is nothing but 1. So essentially, what we end up boiling down is, so we're maximizing lambda. So that means the eigenvalue, the maximum eigenvalue, is the most significant vector in our projection. So suppose we have, let's say we get the eigenvalues lambda 1, lambda 2, and lambda 3, such that, let's just say lambda 1 is 7, lambda 2 is 4, and lambda 3 is, let's say, 1. So that means the eigenvector associated with lambda 1 is the most important singular value. Is the most, not singular value, is the most important vector that captures the most amount of information. So now that we've done this, I'll show you how we derive the SVD formula from this. So my point of showing you this is to show that the optimization problem, where we're trying to find the vector that captures the maximum amount of information, essentially boils down to just calculating the eigenvectors and eigenvalues. So now with that information, we're going to proceed further. So far what we've proven is when we want to maximize this quantity AV, is essentially we just have to find the eigenvalues and eigenvectors. That's the solution to this. Now, since we know that we're finding maximum lambda, so that means AV is nothing but the length of the vector, I told you V. And we know that the length of the vector is essentially the eigenvalue lambda. That's what we were proving. That's what the optimization proved. So since we have that, we now lambda is the squared length. Sorry, not the regular length, but the squared length. So what we need to do instead is we need to take the square root to get the actual length. So let's call this sigma. So this is the singular value. So this is nothing but square root of lambda. And as we showed before, lambda is actually the squared distance, not the regular distance. So to get the actual length, we just need to take the square root. So we've proven that the length of AV is sigma. So now we have, now we need to find our U. So U is also another orthogonal matrix, right? So let's just take V1. So let's say V1, let's take V1 initially, and its associated singular value is sigma 1. So we know that U, and let's call this corresponding U, U1. We're taking only one vector for now, then we'll get into the matrix. So we know U1 is an orthogonal matrix. So that means U1 has to also be orthogonal. That means it has to be a unit length of unit length. So we know U1 will be equal to AV1 by sigma 1. Now if you just rearrange this, we get AV1 is equal to sigma 1 U1. So the matrix V will end up being V1, V2, dot, 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 of how many ever there. And the dimension of this would be D cross. Suppose A is M cross N. So this will be D cross N. Your singular value, which will be sigma, will just be sigma 1, sigma 2, dot, 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 sigma D. The rest of the entries are 0. So this is D cross D. And our U1, not U1, our U matrix is going to be of dimension M cross D. And this is essentially U1, U2, U3. And this is how we calculate the values of U1, U2, and U3. So using this, we essentially break it down to A is equal to U sigma V transpose. Now you might be wondering why it's V transpose. So we know that A V1 is equal to sigma 1 U1. So if you just take it as full matrices, so it's essentially AV is equal to U sigma. Now, so this means A is equal to U sigma V inverse. Now there's a property in orthogonal matrix. So essentially the inverse of an orthogonal matrix is nothing but its transpose. So this implies we get our matrix A, which is M cross N, will be equal to U sigma V transpose, where U is M cross D, sigma is D cross D, and V transpose is nothing but D cross N. So this is SVD, and this is how we get the formula. Now I'll just talk about a few applications of SVD. So we've gotten our matrix A, which is U sigma V transpose. This is M cross N. This is U, so this is M cross D, D cross D, and D cross N. So now, assuming we've calculated D for all the eigenvalues and eigenvectors, so let me talk about an application. So let's talk about like image compression. So what we can do is we can take a new matrix A dash M cross N. So let's say we take only the first 3 important components. So essentially what we can do is, instead of taking the entire D singular values, we can just take 3 of them. So we can take this as m cross 3. We can take sigma as 3 cross 3 because we're taking only the first 3. And then V transpose will just be 3 cross n. So in this way, we can get a good approximation. So I've written some code and I'm going to show it to you and how exactly this works. So let me just share my screen. Just give me a second. All right. So here I've got a picture of a duck. I've stored it here. I'm using Google Colab. And here's our original image. So we've got 544 by 471 pixels. And since it's RGB, it's 3. So for now, let's just take a grayscale image. So if we've gotten it, so essentially we get our A matrix as this. So these are the values. So we're going to do singular value decomposition. This can be achieved using this code. And I'm just going to print out the shapes. And these are the first 10 singular values. So we got U as 544471, S is 471, and this is 471 by 471. So now, if we just plot the singular values, we can see that once we've sorted it, after beyond 1 point, it doesn't affect it that much. The values are too insignificant. So in this code over here, what I've done is, here we've taken if we remember here, I took 3. So instead of taking 3, I've tried different values. I've tried 5, 10, 20, 50, 100, and 471. So on the extreme left is when we just take 5. On k is equal to 10, we can see the image does get clearer. And at 20, we can see that it's a duck. And if you look at 50, it's practically, we can clearly see like it's a duck. We can identify it. And if you look at 100 and 471, there isn't much difference from 50. So as we can see, we don't need all the entire 471 feature space. We've reduced it, but we've still got almost the same image. So this way, it's very useful. This is like one of the applications of SVD. It's very useful for compression. I hope you guys enjoyed this video. That's it for the SVD part. If you guys want anything else, do let me know. Please give this video a like. And yeah, if you feel like I've missed anything or you want me to cover anything else, please leave it in the comments. Thank you.